to put the exam, the third exam, on the Monday after Thanksgiving break. And people didn't like that. Well, you ruined my whole Thanksgiving break. I had to study the whole time, right? So now I put it before Thanksgiving, and the sections just worked out nice so that it was a good break point for the Friday before Thanksgiving break. Right?
Are we section D or C?
You're section D. The one that doesn't have any signatures on it yet.
I remember saying C last time.
Yeah, and you got counted off. Yeah. Okay, so just keep in mind that's coming up. Now, any questions about hypothesis testing for one sample proportions problems? That was section 10.4. Any questions? Easy peasy? All right. Then today we will go on to section 10.7. We're going to skip 10.5 and 10.6. 10.5 is tests for variances. We haven't done any of those all along. And then 10.6 is called the chi-square goodness of fit test. Right? So we're going to skip that. We're going to go to the test today, which is called the chi-square test for association. And so, let me get up to the right page here. The chi-square test for association, we've had tests for means, we've had tests for proportions, and so far that's all we've had. All right. In chapter 11, we will do 2 means and 2 proportions. And this really fits, I think, better as 2 proportions. But we do it in chapter 10, so that's okay. But it applies to contingency tables. You remember what a contingency table is? Man, I've heard that word somewhere. Contingency table. That's right. So you have 2 categorical variables. You put one of them on the rows and one on the columns, and you get what's called a cross-tabulation between the levels of the 2 categorical variables. All right? And then inside the table are the number of people that had this combination of those levels. All right? So a chi-square test is a way to test to see if there is association between those 2 categorical variables. All right? So association between 2 categorical variables. Can't really spell today. Categorical variables. Okay? Now, early in this slide presentation, which I will post on D2L for you, it'll have all of the formulas and the assumptions and the null hypotheses and all that kind of stuff. We'll go through the hypotheses right now, but we're going to do it in the context of a problem from your data. All right? Can you think of 2 categorical variables you collected? We had more than 2, but give me 2.
Gender.
Okay, gender was 1. And smoking was 1. Do you think there's an association between gender and smoking? That's what this test would let us know, right? We would be able to form a test. Does it seem like gender is associated with smoking? We also had exercise. What do you think about smoking and exercise? Do you think there'd be an association between smoking? Okay. And what does that mean exactly, association? It means, okay, a trend between values of one and values of the other. If certain values of one variable tend to occur more often with certain values of the other variable, then we call that association. If it's categorical, so both exercising and smoking have yes, no as their categories, right? So if yeses for exercise tend to occur more often with, what do you think? No's for smoking or yeses for smoking? No's for smoking. If they do tend to occur more often that way, then that would be association. So let's go look at that table. And it's clear down at the bottom here. There. So I'm going to leave the screen up where we can write on this. Is that good enough? Can you read what that says? Okay. So this is smoke. So these are non-smokers. And these are smokers. Right? And then no, yes, or exercise. Non-exercisers, exercisers. Okay? What do you think? Do you see an association? What does your eyeball test say? Well, it's difficult to just look at the numbers in a table. I can look at the number who exercise. 206 of the non-smokers exercise. 12 of the smokers exercise. Those numbers are really different, but that's not enough because these numbers are also really different. I had a lot more non-smokers to choose from. So I need to convert to proportions, right? So remember way back when we did probability? And you remember it all, right? What's the probability of exercising, call that E, given they're a smoker? Compute that probability for me. And you're going to need your calculator, so you might as well get them out now. Yeah. I should say no, because this is not your first time down this road. Okay. Compute this probability. Probability they exercise given they're a smoker. What two numbers do you divide? Okay, that you're giving me the formula. Just numbers in this table. What two numbers? You were right, but
12 and 39.
12 and 39. Very good. 12 divided by 39. Right? I have mentioned, right, that the final is comprehensive. Okay, give me this as a decimal.
0.3077.
Give me one more place.
It would be 0.30769.
30769. Okay? Now, do the same thing for non-smokers. What's the probability or the proportion of exercisers given they're a non-smoker? And remember the S with the C up there means complement. So, smoker, not. Right? Non-smokers. Now what two numbers do you divide? 206 over 326. Everybody understanding that? Okay. Give me that as a decimal.
0.6319.
Give me 5 places.
It's 901 after that.
901, so it's like that. Okay. Now, if there was no association between smoking and exercise, what would you expect to see? If it didn't matter whether or not they were a smoker as to whether or not they exercised, you'd expect them to be the same. The eyeball test says what? They're not the same. They're not anywhere close to the same. This number's more than double that number. Right? So more than twice as many people exercise when they're a non-smoker than when they are a smoker. Okay? So for a test of association, what would our null hypothesis be? What does null mean again? The word null means none, right? So test for association, the null would be
No.
none association. That's bad English, so no association, right? So we write it this way. The book, instead of saying no association, the book says they are independent. Either way is fine. It means the same thing. So I'm going to write it their way and then in parentheses. So the null hypothesis, there... no, I don't want to start with there. That would be my way of saying it. Well, I'll start. The variable smoking is independent of exercising. And then in parentheses, I'll say no association. Okay, so that's your null hypothesis. Up to this point, we've always said, okay, define your null and alternative hypotheses, and use Greek letters and numbers and equal signs and all that. For the chi-square test, it's more complicated than that. We have to make it general, and so there would be too many. These are proportions, right? Those are proportions over there. But we'll end up with 4 proportions instead of 2, and I don't know how to write that. So we just bail out, write an English statement. The variable smoking is independent of the variable exercising, right? Or you could say there is no association between smoking and exercising. So what would the alternative be?
There is an association.
There is an association. So in their words, instead of being independent, they would be dependent. So smoking and exercising are dependent. There is an association. You can write it either way you want. It means the same thing. You can use independent and dependent, or you can use no association and association. Either way, right? The key is to talk about which 2 variables your scenario involves. Here it's smoking and exercising. So don't just say they are independent, they are dependent. Say smoking and exercising are independent, right? To get full credit. All right? So now, which of these hypotheses do these values support? There is an association. Because if there was not an association, we would expect these to be the same. The same. The same as what? Well, the same as each other. But what would that be? That value equal, right? So if null is true, we expect, right? We would expect to see that the probability of exercise given they smoke is equal to the probability of exercise given they don't smoke, and that's equal to what? I mean, yeah, they have to be the same, but the same as each other. But also, what's that value going to be?
0.
No, I wouldn't expect it to be 0. I wouldn't expect it to be 0.5 necessarily. Right? That's usually the first guess, is 0.5. But how many people exercise in this data? If I ignore smoking, and I randomly choose one of these 365 people, what's the probability they're an exerciser?
60%.
Okay, and how'd you get that number?
Just 218.
Okay. And what is that number? It's the probability of exercising without conditioning on smoking. So ignoring smoking altogether, right? So that number is 218 over 365, right? What Stephen said. Does everybody see where the 218 comes from? That's how many exercisers there are. So if I ignore smoking, I just total. So I take that column total, divide by the grand total, and I get this number. Now, what is that number as a decimal?
0.59726.
59726. Okay? Now, here's your challenge. I'm going to mark these so that I can turn this projector off. And your challenge is to fill in the table with the numbers that would make the null true. Make this statement true. Okay? So, you have been challenged. We see the numbers that are in there. Let's see what the numbers would be that would make the null hypothesis true. And the condition is you got to add to the right numbers. The row totals have to be correct. The column totals have to be correct. But the ones inside do not have to match what we actually observed. I want them to be set up so that the probability, the conditional probabilities, are all equal to 0.59726. How in the world am I going to do that? Math, yeah. I hate math. Well, you can figure that out, right? Let's take this one. I want it to be equal to 218 over 365, right? So that one is the number in this cell, which was a 12, right? This is my yes, yes cell, right? And that's what this is. Yes, they exercise. Yes, they smoke. So the yes, yes cell, call it E for expected, right? E for expected divided by the row total. That's how we did that. The number that's in that cell divided by the total over 39 is equal to 218 over 365. Solve for E. I know it's tough, but you can do it. So E equals, how do I solve for E? Multiply through. So I get 39 times 218 divided by 365. What is that? Say it again. 23.293. We'll stop at 3 places. Okay?
Times 39 by the 218 over 365.
Say it again.
I didn't do your equation. I just did 218 over 365 times 39.
Yeah, same thing. It's all order isn't important here. Order that you do the division is important, but as long as it's last, you're all right. Okay? So essentially what this is, it's 0.59726, which is this number, times 39, which is the row total. So what I'm saying is, okay, if I need both of those numbers to give me conditional proportions equal to 59.7%, then what's 59.7% of 39? Well, it's 23.293. So that's my expected value, 23.293. Do the same thing for this cell. See if you can figure out how to do it. What would you expect if the null were true? In other words, do this one, but that one still has to be 218 over 365. Right? So mimic this, but now it isn't a 39, it's a what? 326. Right? Do that and tell me what you get. You got it, Tyler? 194.707. Is everybody getting those? Getting that same number? Okay. What do you notice those two numbers add up to? 218. Right? So that's what I said. That was your challenge. Come up with numbers in here that have the correct proportion if the null were true, but have the right sums. Now, how can I get the other two cells? You could get by subtraction. Or you could get simply by doing exactly the same thing, but now it's the proportion they don't exercise. Right? Well, notice what we did here. Where did this 39 come from? What'd you say? Okay, so it was the row total of smokers. Where did the 218 come from? Total number of exercises. So it's a column total. And where did the 365 come from? That's the overall total or the sample size in. Right? Sometimes I write it as in, sometimes I write it as grand total from the table. So no matter which cell in the table you want the expected value of, you just take the column total times the row total, divide by the grand total, and you get that number. So do this one that way. Now we already said you could get it by subtraction, and that's fine. But Rachel, you got it? Well, get it.
Can you repeat what you said? Column total plus row total divided by...
I said this.
Yeah.
Do that. 131.293. Okay? And then the last one, I don't care how you get it, just give me this number by subtraction or by doing the row total, column total over grand total. 15.707. Okay? Notice that all the additions work. 131 plus 194 gives you 326. 1523 gives you 39. Adding columns, it gives you 147, 218. Right? So everything here adds exactly to what the observed table added to, but the numbers inside the table have been shifted around to make this exactly true. Right? To make the null true so that those conditional probabilities are exactly equal to each other. Right? This is how we've been doing hypothesis tests. Right? We said, okay, what's your null hypothesis? The null hypothesis, if it's a means problem, is that the population mean is some number. And then we collect data and we see how well does our data match to what we expected if the null were true. If the null were true, we would expect the mean to be this number, but my sample data, I got this mean, and I compare them. Right? I compute a test statistic that measures how close the sample data is to the hypothesized data. That's exactly what we're going to do here. Let me turn back on the projector, and it'll put the observed counts back in there. I tried to write low enough that they won't overlap. Oh, good. See how good I was. So in this cell, we saw 120 subjects who were non-smokers and did not exercise. But if the null were true, we would have expected 131 in that cell. They don't match very good. We got 11 too many in this, or 11 too few in this cell in our observed data. So guess what we got here? 11 too many, right? Because they have to add to the same. What do we get here? A little more than 11 too many and 11 too few, right? So the way then we in a contingency table decide how well the observed data matches the expected data is with the chi-square test statistic. And the chi-square test statistic, actually it's on this slideshow in a lot neater handwriting than mine. So let me scroll back to that. Did that. There. So the chi-square test statistic, it just looks like an X, but it's kind of got these curly ends on it. That's a chi, right? So chi-square equal. What does that symbol mean? Summation. So this means sum over all of the cells of the table. So I've got 4 things to sum up. Sum those 4 things, the observed value minus the expected value, square that, and then divide by the expected value. So in our data, that first cell, let's write it down here, chi-square equal, the first cell was 120, and the expected value was 131, and I forgot what? 293? 131.293. Square that and divide by 131.293. And that's the first cell. And I got how many cells? 4. So plus. Then you do that same thing for all 4 of the cells. And I'm not going to take the time to go through and actually sum them up. In this slideshow, they have some examples where they do show every single one. But guess what?
There's a function on our calculator.
And I know you're thinking, God, I hope my calculator can do this. Yes, it can. Right? So your calculator will compute this. Now this is a test statistic. Unfortunately, this test statistic does not have the intuitive appeal that the previous ones did. Before we had a t test statistic or a z test statistic, and we said this is the number of standard errors that the observed data is from the null hypothesis. This is not number of standard errors. You get a number back, that number has no meaning to me, it has no intuition, so it's just a number, and I have to rely on my calculator with the chi-square distribution to decide, is it extreme or is it about what you would expect? And we do all that through p-value. So the book will walk you through the whole process of a rejection region, looking up in a chi-square table a critical value for this test statistic. But you don't have to do any of that. We're going to go right to the calculator to do this. Okay? All right, so let's do it. Okay, so here's where we start this. No, next slide shows what or says what I want you to do. Based on this data, is there enough evidence at the 0.01 level of significance to say that there is a relationship between a person's choice to smoke and their choice to exercise? Now, I intentionally used the word relationship instead of association, just so you get used to the fact it means the same thing. That's what they mean. When they say relationship between 2 variables, that means an association. It means they're not independent. Right? Answer by performing a chi-square test for association. It's also called a chi-square test for independence. So those two mean the same thing. All right, so step 1 is always to state the null and alternative hypotheses. We already did that right here. So step number 2, determine which distribution to use. What's our distribution this time? Chi-square distribution, right? I don't really care that you know anything about the chi-square distribution, but remember, I always substitute what for distribution? What did I say we do for that step? Decide which function on your calculator you're going to use. You're going to use the chi-square test. Okay, and it is on the calculator. Then you're also supposed to state the level of significance, and they said to use alpha equal 0.01. Okay? Now there are assumptions that have to be met. So that's part of deciding. So let's talk about those assumptions. First assumption is always what? Random sampling. Right? So one, data come from a random sample. What about this data on smoking and exercising? Did it come from a random sample? No. Your sample was not random, right? So we don't meet this assumption, but we're going to ignore that. Technically, we don't meet the random sample assumption, but we're going to say, well, when you pull them all together, we'll call it good, right? Then the second assumption, this technically a contingency table problem is a form of a proportions problem, right? Because it's proportion in this column, and then but remember for proportions what the sample size requirement was? Remember the NP greater than or equal to 5 thing? Same idea. NP is the expected number of successes, and then expected number of failures has to be at least 5. Well, now it's a contingency table, and in the smokers row, we got exercise, not exercise. So I got failures and successes, and they have to both be 5. Expected values have to be 5. And then in the other row, 5. So every cell has to have an expected value of at least 5. Expected value is greater than or equal to 5 for all cells of the table. Okay? Now, notice it says expected values, not observed values. You can get a table from your data and see, oh, one of those cells only has 4 in it. Well, that's okay as long as the null would say, well, there ought to be 6 in there, right? Then you're still okay. But we'll look at an example of that in a second. So those are your assumptions. In ours, did we meet the expected counts were all at least 5? Yep, there they are. And the smallest one is a 15.7. Now, when you're actually doing one of these on the test on the 20th, you won't know those expected values till you get done doing the test. So then you go back and answer that question, right? So I run the test, I look at my expected values, I see that they were all at least 5, so then I can go back and say, yes, that assumption was met, right? Okay, next step. Gather the data and calculate the necessary sample statistics. Well, we've got the data, and now we're going to use our TI-83 calculator, and it will calculate those expected values for us as we go through the test. So here's what you do. Get your calculators warmed up. Press the second function button, and then the X inverse button. And that's over on the left-hand side, and it has an X with an exponent of -1. So X inverse. And it has the word matrix above that button. So it's second function, then matrix. Everybody got it? And when you do that, you should get a menu across the top that'll say names, and then math, I think, and then edit. And you want to go over to edit. And then the first one should be highlighted, number 1, A. So it's got brackets A, and that means matrix A. Right? So press enter on matrix A. And always use matrix A. And you'll see why in a second. That makes it so you don't have to change to a different matrix, and it's hard to do at a later step. So just always use matrix A. Okay? So when you do that, you should see this screen. You're going to enter 2, press enter. It'll jump to here, enter another 2. So what does the 2 by 2 mean? 2 rows, 2 columns. And it always goes rows by columns. Right? So it's rows, we'll call R. Columns, we'll call C. It's always R by C. Okay? And then type in the numbers that you see up here that we had in our table a minute ago. 120, 206 on the first row, 27, and 12 on the second row. And once you get that entered, you're now done with this screen. So the next step is to press the Stat button. Go over to Tests. And go down to chi-square test. Now it's almost all the way to the bottom. So you can actually get there faster if you go up, and it'll scroll around to the bottom and come up. But that's up to you. So it's kind of hard to tell. The calculator is even worse at writing one of these Greek chi's than I am. That is a chi, right? It kind of looks like an X, but they tried to stretch it a little bit. So chi-square test, right? The one right below it is chi-square goodness of fit test, GOF. And that's section 10.6, which we skipped. So we won't use that one in this class. If you get that one by mistake, hopefully you'll see, well, this doesn't match what I'm used to seeing, and then hopefully you'll catch that mistake. So it's just chi-square test. So press enter on that. And then you should see this screen. It'll say observed A, expected B, and then calculate or draw. And this draw, I haven't talked about draw, but all of the hypothesis tests have that choice. And it draws a picture of the distribution and shades the tail where the p-value is. Which is helpful when you're trying to learn what you're doing. But right? So you want it to say A because that's where you put your data. And that's why I said always use matrix A so you don't have to figure out how to change that because it isn't real easy. But you can change it by using the names. When you went into matrix, there were the 3 menus, and the first one was names. Use that, and you can put them in there. But as long as you use A, you'll be fine. And B is where the calculator is going to store the expected counts. Yes?
If we have a matrix in B already from like a previous class, like, do we need to erase that matrix?
No, it will overwrite that matrix. That's a good question. I mean, it's funny, you know, sometimes I'm kind of an idiot. And the first semester or two that I taught this class using this calculator, I didn't realize that it was going to compute them and put them in B for me. I thought I had to compute them by hand, put them in B, so that it had the observed and it had the expected, and it could compute what it needs to compute. And then finally a student said, you know, you don't have to do that. It just does them. It puts them in there. So it overwrites whatever's in there. It was overwriting the same numbers that I was putting in there, and I never knew the difference. But, right? So just leave it like that. You don't really have to do anything on this screen. As long as you use A, go down and hit calculate. When you do that, you should see this screen pop up. Okay? So you should have chi-square, that's the test statistic, equal 15.221. That number, again, that has no intuitive appeal, but that's this one. If we had done the other 3 terms and added it all up, we would have gotten 15.221. Okay? And then you see a p-value of 9.56. So what's the conclusion? Is that less than alpha equal 0.01?
You're having the -5.
Yeah, I'm seeing a few catching on. 9.56, that makes no sense to be a p-value because a p-value stands for probability. It's got to be a number less than 1. So you look out over here and you see E negative 5. So that's 9.56 times 10 to the negative 5th power, or 0.0000956. Right? Now, what is a p-value again? I keep forgetting that. It's probability of something. It's okay, I can wait. Okay, good. The probability of getting what you observed, or even further from the null, if, what's the if part? If the null is true, right? So what does this say? If the null is true, if there's really no association between smoking and exercise, you pretty much can't get data like you got. So if you can't get data like this when the null's true, but I did get data like this, the null must not be true. So I'm going to reject it. And we're going to reject it. If you don't have the intuitive sense of that, hopefully it will come. But if the p-value is less than alpha, you reject the null. And our alpha was 0.01. That's clearly less than 0.01. So what's our conclusion? Remember, rejecting the null is not your full conclusion. You have to go back and talk about the hypotheses and in the context of the problem. So what is our conclusion? We know we're going to reject the null. That's called our decision. Reject the null. What's the conclusion? And I'll write it over here. How does that sentence always start? There is blank evidence, right? So there is or there is not. Which is it? Is, right? There is. And you always talk about the alternative hypothesis. I'm going to reject the null, so there is evidence for the alternative. If I don't reject the null, then there is not evidence for the alternative. Got it? So there is sufficient evidence to conclude, and then you basically just write out whatever your alternative is. To conclude there is an association, or you could say smoking and exercising are not independent, or they are dependent, however you want to write it. There is an association between smoking and exercising. Okay? And you have to write it all the way out like this to get full points. If on the test you write, there is sufficient evidence to conclude there is an association, period. -1. Right? Association between what? I got to know that you know what it is you're actually testing. I'm testing to see if my row variable, which was smoking, and my column variable, which is exercising, seem to be related, or if they seem to be independent. Right? We have evidence to say they're related or associated. Okay, now go in and look at matrix B. Go second function matrix, go over to edit, and then go down to B and press enter. You should see these numbers. All right? Now, once you see these numbers, then you can go back and check this assumption. All expected values are at least 5. All right? Some problems will be, some problems won't be. I want to do another example, but I looked at the screen and I saw this, which reminded me, oh, I haven't talked about degrees of freedom yet. Degrees of freedom are not that critical for what we're going to do because we're not looking up things in a chi-square table. We're just using our calculator. But the degrees of freedom are R minus 1 times C minus 1. Okay, so this table has a 2 by 2 table, so I have a 1 times 1, or 1 degree of freedom. Right? And what degrees of freedom is simply how many of the cells in the table do I have to fill in before all the rest could be filled in by subtraction. And when I give you one number, if I give you this 194.7, then you can get this one by subtraction. And if you can get this one, then you can get this one by subtraction. And then when you got this one, you can get that one by subtraction. So you can get all the rest. There's 1 degree of freedom.
So all contingency tables will have a degree of freedom of 1.
No.
If you have 2.
All contingency tables have a degree of freedom of number of rows it has minus 1 times number of columns it has minus 1. Let me do a real quick illustration. Let's say I had a 3 by 4 table, right? And I know my row totals, I know my column totals. They're fixed numbers. If I fill in this cell, can I get any others by subtraction? No. So I got to fill in another one. If I fill in that one? No. How about if I fill in this one? Now I can get one. I can get this one. Any others? Nope. So let's fill in another one. Yeah, now I can get this one. But I still can't fill in the rest of the table. So I'm still free to choose numbers, right? So I fill in this one. That then locks this one. There's no freedom for that one. And then any others? No? So I fill in one more. And now we get all the rest. Now I can get this one. Subtracting that way, I can get this one. And now that I have these two, I can get this one. So what's my degrees of freedom? 6, which is 3 minus 1 times 4 minus 1, or 2 times 3. Okay? That's degrees of freedom. Okay. Now, I'm going to run out of time, so we won't have time to work this all the way through, but I wanted to look at this contingency table. This is, again, from your data. This is exercise by health rating. So these are no to exercise, yes to exercise, and then poor health, fair health, good, very good, excellent. Right? To do a chi-square test of association, we'd be testing the null hypothesis. There is no association between whether or not people exercise and how they rate their health. The alternative would be there is an association. What do you think about expected counts being at least 5? Look at this column. Remember what we did before. We have to make these two numbers add up to there. Well, there's no way to make these two numbers add to 1 and have at least 5 in both of them. Right? So this is clearly not going to work for chi-squared test. So in this situation, what happens a lot in practice, if I were going to analyze this data, I'd say, well, I'm going to collapse these first two columns. I'm going to push this one person over into there. So this would be 22 plus 0, 10 plus 1, or 11, and there'd be 33 people in this column. Then I'd have expected counts all of 5, and good to go. Now, again, these are observed counts, not expected, but you can kind of tell whether or not you're going to have a problem. But when you go do the chi-square test, then you go back and look at matrix B to decide, yeah, look, they were all actually greater than 5, so we're okay. All right? So what are the dimensions of this? Say we collapse this first one into here. What would the dimensions of the matrix be? 2 by 4. So you'd go into matrix A, edit, 2 by 4, and it would then give you enough space for that, entered in, and you could do your chi-square test. All right?
So if there's more than one row that doesn't equal 5,
Don't worry about the collapsing one. I'm not going to give you any like that, but just know that there are times when you don't get enough to do it. So, okay, we will see you on Wednesday. Don't forget, tonight you have 10.4 homework due.